So we'll be studying today the okay. So today we'll be studying how to design of rotor bars and slots and about the entering current, design of rotor bars and slots. So before going to the design of the rotor bars and the design of the slots, so there would be four categories that we will be interested to know. The number one thing we would be interested to know is the how to calculate the rotor bar current, and then are you the only person, Ratika? Hello.
No, sir. Four people are there.
Okay, okay, very nice. Area of rotor bar. How do we go about the area of the rotor bar? The third factor would be to shape and size of rotor slots and slot insulation. So shape and size of rotor slots and slot insulation. So in order to go for this calculation, first of all we have to understand what is the rotor bar current. So when we are talking about the rotor bar current, so how do we calculate the rotor bar current basically? So before going to the rotor bar current as such, let's assume certain factors. Let ms be equal to number of phases, that is number of phases in stator, because basically when you are giving the supply to an induction motor, you are giving the supply to the stator. So number of phases in stator, and the primary mmf that is getting developed due to this is getting developed in the stator, and from that stator only the mmf is passed on to the rotor due to the air gap, and this interaction between the rotor and the stator with the distance of slip leads to the rotation of the induction machine. This is primarily what exactly it's happening. So is is the stator current per phase. So this is the stator current per phase, and you have ts, that is number of stator turns per phase. Ts is equal to number of stator turns per phase, number of stator turns per phase. And then you have SR, that you can write as number of rotor slots. So one more term that we'll be incorporating here would be your SR, that you can write as number of rotor slots. So this number of rotor slots is essentially but nothing but the number of rotor conductors. The number of slots is equal to, because each slot will have some conductors. Whenever we say, last time also I did a problem, it is having 72 slots and each slot is carrying 20 conductors. So the total number of conductors would be, if every slot is having only one conductor, the number of rotor slots would be equal to the number of rotor conductors. But if it is having more conductors per slot, then you have to multiply that. So here let's suppose that every slot is having only one conductor. Usually it's not the case, but for this derivation, let's see number of rotor slots is equal to number of conductors conductors and this number of conductors would be equal to the bars in the rotor. See, when you are drawing the rotor, the squirrel cage, the name is there because if you see there is an, it's like a squirrel shaped, like this. Your rotor is there, and the rotor has end rings, which is shorted. So these rings are there the, at the end. This you can see. These are the end rings, and these are the bars. These are the bars. So we are interested to calculate the current IB, the bar current, and also interested to calculate the current in these rings. This is called end rings. So first we'll in this case we'll analyze how do we go for this current, that is the bar current. So in order to go to the bar current, we have to come through stator. Okay. So this essentially is equal to the number of rotor bars. So this would be a number of rotor bars. So like every slot would be there, but the number of rotor turns. So the turns would be equal to the rotor slots divided by two, number of turns, because two turns form you one conductor. Okay. So the for one turn will have one half of a conductor. So you can write safely write your number of turns, or you can write here if you want, write your number of turns would be equal to SR divided by 2. So your number of turns would be equal to this. And now let's come to the bar current. So the bar current IB, this is the bar current, is the rotor bar current. This is rotor bar current. This is in amps. You have to. So how do you go about this? Now tell me the stator MMF. The MMF established in stator would be equal, because it's a three-phase stator. So the MMF established there would be equal to how much? So if we see the MMF established in the stator, so MMF established in the stator, if we have to write the MMF established in stator, so MMF is basically ampere turns, or number of turns into current. So we know the number of turns are for stator current is Is, number of turns we have already given Ts. So this is ampere turns essentially. But it's a three-phase stator, so you have to take into account the number of phases also. So where Ms is what? Ms is, see here, where Ms is equal to number of phases in stator here. And your Is is stator current per phase, Ts is number of stator turns per phase. So these things you have to substitute over here, Ms, Is and Ts. So once you get this Ms, Is and Ts, then you have to go for the total MMF, total rotor MMF. So now this is the MMF getting established in the stator. Now let's go for the total rotor MMF. Can anybody tell me? I will total rotor MMF. Yeah. Can anybody tell me how much it would be? Total rotor MMF. Seeing from this, see here. MMF in the rotor would be equal. See, MMF is basically what? Number of turns multiplied by what? Current. Okay. This is MMF. This is basically MMF is what it is. Now in the rotor, we just saw the number of turns for the rotor is SR by 2. Okay. And the current that is getting established in the rotor is IB. So you can write MMF established in the rotor is multiplication of these two terms, because the number of turns mmf is basically number of turns. So we have sr by 2 as number of turns into current we have, so ib. So can we write total rotor mmf is equal to sr by 2, that is your uh, sr by 2 into your ib. So here you got the total rotor mmf. So one more thing, as far as the mmf of rotor is concerned, if you carefully analyze, so mmf that is entering in the stator has a certain relationship with the mmf that is entering in the rotor. So that relationship is, there is some efficiency of an induction with the efficiency. So usually if you see the induction machine, so it has around 80 to 85% efficiency. So that means the input side, the mmf that is entering is the stator mmf, and the output side you get the rotor mmf. So we can safely say that the rotor mmf is equivalent to 85% of the stator mmf. So we can write down, assuming assuming, assuming rotor mmf is equal to 85% of stator stator mmf, of stator mmf. So this is like of stator mmf, wherein we can write ib into sr by 2 is equal to 0.85 ms is into ts. So this can be written. So from here we can safely calculate ib here. 2 will ib in terms of, so this ms we know it's a three phase, 0.85, so into 3 instead of ms into is ts. So this 2 goes up and sr comes down, so sr by 2 cross multiplication. So we end up ib as ib we will end up as ib is equal to now 0.85 into 6 into is ts divided by sr, so ampere. So this is our final expression for this term. This is the current in the bar magnet. So uh, the now the area of the rotor bar we have to calculate. The second term that we will be interested is would be to calculate the area of the rotor bar. So let's go for the area of rotor bar. So in order to calculate the area of the rotor bar, so the value of the rotor resistance depends upon current density and number of rotor bars. So basically what happens is the value of your of rotor resistance depends upon current density and number of rotor bars and number of rotor bars. So see here, basically what I mean to say is that we have this, if your what happens to the current density, the cross sectional area of bar decreases. Suppose uh, when current density increases, okay, so current density increases. If your current density increases, so what will happen to the cross sectional of bar? So cross sectional of bar has to decrease, because current density is what, I by a, current by a. So if it has to increase, your area has to decrease, where this is your current density, and this expression is for the area. So area has to go down. So because current density is your current by area. Okay. So that thing you have to keep into mind. And when you are this thing current density increases, cross section of bar decreases. So which gives increase in resistance. So this would happen. When this happens, it what will happen to the resistance? Resistance increases, where this is resistance. So resistance increases. So again, if the resistance will increase, what happens to the starting torque? So if the resistance is increasing, starting torque would increase. So torque would again starting. This is the starting torque. So to control the torque, basically, we have many methods in induction motor that we have studied in previous sections. One of the method is also the resistance method. So starting torque increases. On the other hand, so what happens due to increase in current and resistance? If you are simultaneously increasing the resistance and current, so I square R loss would be there. So your copper loss becomes more. So if your copper loss is becoming more, then what happens is that your efficiency is output by input. Okay. So in the input side, your losses are increasing, so that means your efficiency will go down. So that things you have to keep in mind. So here I will write down one thing. I write down, yeah. Let AB is equal to your section of each bar in millimeter square. IB is equal to current through each bar. This is your current through each bar. Okay. And your del V is equal to current density for bars. This is the current density for bars. So this would be around 4 to 7 ampere per millimeter square usually. And then now you have the shape and size of the rotor bar. So how do we go about the different type of shapes and sizes of the rotor bar? So uh, so we'll go for the shape and size. So there are different shapes. One of the shape is like this. Okay. Another shape you have is in this form. Another shape. Basically, this is the shape and size of rotor slots. This is the shape and size of rotor slot. So why are we using these type of shapes? See, this type of shape, you can see there is this is an open. If you can see, this is the open type of, or the semi-closed slots. So this we'll call as the semi-closed, whereas this is the closed ones. So this is called as semi-closed. These two semi closed, and this yellow and this black, this is the closed. So when to use closed slots and when to use semi-closed slots? See what basically is happening is your it depends. See your resistance. If you write down resistance is equal to rho L by A. So what you have seen, or we can write down your mu is equal to 1 by rho. So we can write again your resistance is equal to 1 by mu A, sorry, L by mu A. So L by mu A, that is your Lg. This would be your air gap length. So you can see if your resistance is decreasing, only in the case your air gap length will decrease, that you have seen in the phasor diagram also last time what I designed. Now basically essentially what happens is that for small machines closed slots are incorporated because here reluctance of the flux path is minimum owing to the absence of slot opening. So what we write, this these type of slots that is called as the closed slots, so essentially are used for small machines. So closed slots, wait. Closed slots are used for closed slots are used for small machines. Small machines. So this is the why is the reason are this because large reluctance, because large reluctance of flux path, large reluctance of flux because the large reluctance of flux path is minimum, is is minimum owing to absence of what, tell me, owing to absence of slot opening. So there is no slot opening, so it is minimum. For medium and large size machines, semi-closed slots are used, and these type of slots that are used, the for the other type you have seen here, this two type, these are used for medium and large size machines, and large size machines machines these semi-closed slots are used. Semi-closed slots are used. Now let's go to the point of this slot insulation. Now what is the slot insulation? Slot insulation. So this is the slot insulation. So slot insulation essentially, if you see what happens is that, so there is a semi-closed slot. If I'll be drawing one of the semi-closed slots, and let's see, like previously what we saw. So here inside there is a semi-closed and there is this here. So this is the insulation that we have over here, insulation, and this is the semi-closed slot. Okay. So in case of squirrel cage rotor, the insulation is provided at the top bottom of slot. On the other hand, like a small clearance is clearance of 0.15 to zero point 0.4 mm is provided. So you can see over here, this is the insulation, and there's a small clearance over here. Over here, this is around 0.15 mm to 0.1 mm. So this is the slot insulation in case of a in case of a squirrel cage induction motor. The insulation is provided at top also and bottom, at top and bottom, and an insulation of 0.15 mm to 0.4 mm is provided. Now we have to go to understand what is basically the end ring. Okay, so when we are trying to go for the end ring, to understand the end ring, so what happens is that the stator of the winding of a three-phase induction motor is essentially what it is, a three-phase distributed winding, and it produces a rotating magnetic field. Because the winding is a three-phase distributed winding, you have this. Okay, you have one phase, another phase is there, another phase after an interval of 120 degree. Hmm. Similarly, you have another phase here. Let's say it's not exact. So this is like after a 120 degree interval. So you have this three phase. So what happens is essentially is that these three phases, they are placed 120 degree apart. So now if you have to like draw like them, all the three phases, so this would be the phasor diagram for this. This is 120 degree, this is 120 degree. So if you have a phase R here, R, and another phase is Y, so between R and Y there is 120 degree, and this blue between Y and B this is 120, and between R and B again this is 120. So it's a complete circle. So in the complete circle is 360 degrees. So these three faces are placed 120 degree apart, and these faces, it is responsible to create a rotating magnetic field. So this rotating magnetic field induces EMF in the rotor bars. Now we are interested to know what about the end rings. Now we calculate the current of the this thing of the bar. Now there is current that is getting produced in the end ring. So what happens is that, see, in the end rings there is certainly a direction wherein you can see that your end ring has one end ring is at one side of the rotor bar, another end ring is the bottom of the rotor bar. So they are acting as a north and the south poles, and current is entering from one side of the end ring and current is leaving from the other side of the end ring. So for that I'll be just drawing a little bit. Yeah, so let's clear this frame. So if you have to understand, so this is one end ring. So let this be one end ring, and the other part be, let this be the down part. Very difficult to draw over here. That's so again you have one side is entering, okay, the other side it is leaving. Hmm? And this is your north pole, and this is the, suppose, This is so this is how it is happening. So one side it is entering, another side it is again. Let's draw this. So this is entering, and the other side this is leaving. Same thing you can do this side also. So you see one thing, one mistake I've done. See, basically what happens is that in the end ring, so if this is the side that is, for example, it is entering, okay, and wait 1 second, and at this end, at the very end here, let me make this. And this is the entering end, and this is the leaving end. So once this is entering from here, so all the other sides here, let me do this. Because it's the north pole, so here you will see that the it would be leaving. Okay, now here in the south side it is like entering here, so here it would be leaving. So here it is leaving, and again here also it is leaving. So if you go for the sinusoidal part of it, let's extend it here also, and again through this part. So let this be figure A, and this, no, it's less. Okay, no problem. So this is the, it has to be little sinusoidal. I'm not able to do it here. It's very difficult to draw with this touchpad. So you please try to see, this is the maximum part. So this is entering over here. Okay, this is the positive half cycle, that one there, and here it is leaving. So here then this current is leaving. Now the same thing that has to go down. So please, no, draw. Okay, down. So this would be like in the entering section. So next, see down here, like same towards down here. So I'll draw that part in the next part. So this figure B. So same when in the examination, because I'm not having, so you have to draw down only. So down, what happens is the same thing is following over here. So your entering current would look like, so these two bars are there, bar one, and you have the second bar over there. So you can draw the entering current now from the top portion. So you can clearly see in the one portion it's like this. The entering current from one bar to the other bar. So if you are drawing this part like this, So you'll have clearly the flux path that is mode would be like this for this bar across the bar. Again, for this bar also same thing. So similarly for every bar it would be like this path would be traced. So the flux path would be in this direction, particular direction. So that is like current is like moving like this. Here also moving like this. Again for this also the current is moving like this, and the flux path that you are tracing, it's going from here. So the current direction is essentially like this, entering from here and leaving here. Whereas in the other side, sorry, whereas the other side, this is for the north pole, whereas for the south pole side, if you have to look into that, so again you, this is the bar in the south pole side, you have your current entering from top and leaving the other way around. So here the current was entering from this side, whereas here the current would leave from this side. So it is leaving from this side in in the other case, other scenario, whereas it is entering from top. So here you see this for the south pole case, this for the north pole case. Now how to go about the calculation of the entering current? This was about the diagrammatic view. Now basically what is end ring and area of the end ring, so we'll be listening. So this part you understood, huh, Ratika? So basically what
Yes,
happens,
yes.
huh, because graphical view is there, so that down only we have to create. So for every bar I did not create, I created for one bar, another bar, same thing here for two bars, here for one bar. So if you want to create for 3 4 bars, same thing you can create, or here also you can write from here, it will go from there. So now how to calculate the entering current? Now in order to calculate the entering current, what we have to understand is that there is a certain relationship between the bar current, because current that is entering in the bar and the current that is leaving from the entering, they have certain relationship. So let's, bar current to we already calculated. Let's go for consider a group of rotor bar under one pole pitch. So in order to design of end rings, so what we do is that we consider we consider a group of rotor bars under one pole pitch. We consider a group of rotor bars under one pole pitch. One pole pitch. So one pole pitch is pi d by p. So this is basically your pole pitch. So uh, so one half of bars would send current in one direction, so that you can see that one half of the bar is sending current in one direction and another half of the bar is sending current in another direction. So we can write down that one half one half of bar is sending current in one direction and other half in another direction. So another half in another direction. So to an to another half to an end ring, basically to an end ring, because bars are connected. So end rings are basically the shorting of the bars at the end. If you analyze a squirrel cage induction motor, it is shorted at the end. If you have also the images of it, so you'll see in the lab also you can see. If current through each bar is, see, let's suppose the current through each bar we calculated is IB, or the maximum current through each bar is IB max, and it occurs for all bars at the same time. So the maximum current through the end ring would be, see, basically the maximum current through end ring would be the equal to the pole, that is the, so see, if the current through each bar is, let's suppose the current through each bar is IB max, and it occurs for all bars at same time. That means it occurs for all bars at same time. So the maximum value of the current in end ring. So the end ring current we saw, okay, the end ring is the current in the end ring depends upon the rotor bar current. So the end ring current is over here. If we see, this is the current in the end ring. So these are the end ring. This is the end ring. These are the bars. This is also end ring. So end ring. So there are end ring on the top and the bottom, and this is being shorted. So can you tell me, can you, after this much analysis, can you tell me what can be the maximum current? So see, number of bars per pole. So how many bars are there per pole? So here we can see there are one, two, three. So the number of bars would depend upon, essentially it would depend upon the number of bars per pole divided by 2 into current in the rotor bar. Okay, so maximum value of the end ring current would be equal to, sorry, maximum value of the end ring current. So you have to write the maximum maxi, maximum value of end ring current, it would be equal to what? It would be equal to number of bars per pole, number of bars per pole divided by 2. 2 why? Because you have, see, 1 2, okay, that's the reason. 2 per pole divided into the current, into the current per rotor bar. So that is current per rotor bar is IB. So number of bars per pole. So number of bars per pole divided by 2. So number of bars per pole, that means number of bars would depend upon what? Number of bars would depend upon the number of conductors, or the number of conductors internally would be depending upon the number of rotor slots. So we can safely write that number of bars would be equal to SR per pole divided by P divided by 2, okay, into IB, okay, so into IB max. So in other terms, your end ring current, if you want to express the end ring current, so you can write safely your end ring current, that is your IE max, would be equal to your SR by 2P into IB max. So this is the end expression for end ring current. But we know that the current, see, it will only be possible, this expression is only possible if the current through all the bars is same. That means the current should remain same through all the bars at simultaneously. But is it possible? How? It is not possible, because the current through all the bars is not same, not same. So what we'll do, not same simultaneously, uh, but it obeys a sinusoidal law. So you have the bar, you saw over here also, see, here also. So it is not the same, the current is not remaining the same, the current is obeying your law. See, this is the bar current over here, you can see IB. So is it remaining same? No, it is changing, it is obeying a sinusoidal law. So what we have to write is that we also have to take the same thing when we have to calculate the entering current. So so what we will do is that Hence, the maximum current in the ending is calculated. So, the in order to calculate the maximum current, taking a average value of bar current. Hence, maximum current through an ending. So, the average value we have to take into consideration. Because of this, hence, hence, as I can write down as bar current is not remaining same and same simultaneously, and what is this rubber, A- and has sinusoidal characteristics characteristics. Therefore, average value of bar current is considered. So the average value of the bar current is considered. Now, your I max entering current would be equal to SR by 2P into IB average. Now, the IB average value, see, we know that the average value is equal to 0.636 or 2 by pi. So, IB average is basically, we have studied average value, RMS value. RMS value means maximum value divided by root 2. Average value means 2 by pi of maximum value. So this is like in the first year only we have studied. IB average would be equal to 2 by pi, that is 2 by pi. If you do this, it will come around 0.636. 2 by pi divided by, sorry, 2 by pi into I max. So this would be the value. So this value you have to resubstitute back there. So you will get a IE max value. So this is your IE max value. So this will come around how much? IE max value will come around SR by 2P into 2 by pi into IB max. So this value, if you consider how much this value will come, 2 by pi into SR by 2P into IB max, and the IB max value you can either express this in terms of RMS value. So if you are IRMS, you are writing IRMS, that would be IB max divided by root 2, or IB max you can write root 2 into IB. So you can substitute here that value also. So you will get SR by 2P into 2 by pi into root 2 IB. So when once you are doing this, this two will get cancelled. So the final value which you will be getting over here would be equal to, so here the final value that you get over here, tell me what would be the final value that you will be getting. So the in the next slide we'll see the final value that you will arrive at would be equal to, the final value would be equal to, so now you have IE max is equal to 2 by pi into SR by 2P into root 2 IB. So where what I have done is I have not taken the maximum value, I have taken the where IB is RMS value of bar current, RMS value of bar current. And since entering current values very sinusoidal, that's why I have so again you have, this is the entering current, so this is the IE max. So Since entering current varies, basically what varies sinusoidally. So what I do is that I take RMS value of entering current. So RMS value of entering current. So the RMS value of the entering current, if I'm taking, is that would be E would be equal to, this is E max. So IE would be equal to, that is IE RMS. This is the RMS value would be equal to IE max by root 2. So these quantities over here, I have to 2 by pi into SR by 2p into root 2 IB. I have to divide the whole quantity by root 2. So I'll divide it by root 2. So this is the expression for the entering current which I'll be left with. And my entering current would be equal to C. And this 2 and 2 will also get cancelled. So only terms that are left is SR, that is the number of rotor slots, into IB by pi into P. So I can write my entering current. This is end ring current is equal to my SR IB divided by pi P. So this is like, so SR IB pi by P. This is IE. So this is the expression for the entering current which we got. 4 minutes are only there. I want to do a problem, not possible. So we'll revise a bit. So basically what we studied today is that we studied how to calculate the, yeah, tell me, any doubts? Yeah, anyone having any doubts? Hmm? Ratika?
No, sir.
No, anybody, you got it now? Huh?
Yes, sir.
Okay, so this is the design of the rotor bars and slots. Basically what happens there, this is the rotor bar. So the bar of the rotor is the those connected, and on the downside you can see over here. So these are the end rings. These two end rings are there. So we have to calculate the current and the rotor bars. Essentially, what we do is that we calculate the MMF of the stator. So MMF of the stator, because it's a three-phase machine. So MM of the stator would depend upon the number of phases and the current through it. If the current through it is ISTS, so the total MMF that encounters in the stator would be equal to the number of phases, that is MS IS into TS. Now the MMF that is getting incorporated into the rotor depends upon the number of turns. So the number of turns and the current that is incorporated, number of turns in the rotor are directly proportional to the number of slots. So the number of how many number of rotor slots are there, the number of turns are half of it, because the total number of conductors, one conductor is equal to two slots, or one conductor is equal to two turns. So therefore the number of turns would be equal to SR by 2, and this is IB. So this is the number of turns into the IB. So these SR IB by 2, this is your rotor side MMF. This is your stator side MMF. So what you write down in the next slide is that, let's assume that the rotor side MMF is 85% of the stator side MMF. So you write down your bar magnet current IB into SR by 2 is equal to 0.85 ms ISTS. And when you resubstitute in the equation, you get this thing. And then again, the R is equal to rho L by A, and area of the rotor bars and other parameters. What we saw is, depending upon this, if current density has to increase, area has to go down. Area has to go down, resistance will increase, starting torque will increase, and this depends upon these factors. Then there we saw the different types of slots which we encounter. Closed type of slots are used for small machines, whereas for medium and large size machines we are using semi-closed size machines, and then there is the slot insulation which we went through. Then we figured out how to calculate the entering current. In order to calculate the entering current, we just calculated the maximum value of the entering current. So the maximum value of the entering current would be equal to number of bars per pole. Again, the number of bars would be equal to the number of slots, and which the number of slots are equal to SR by P divided by 2 into IB max. So IB max value, we entering current IE max was SR by 2P into IB max, but IB max we expressed in terms of average value over here. So average value was 2 by pi IB max. So SR by 2P into 2 by pi IB max. Again, we express this in terms of this IE max in terms of its RMS value. And finally, we arrived at this expression. This is SR by IB into pi. This pi P is the entering current. So please give your attendance. Already the time is up. I'll stop recording. Yeah, you can give your attendance as time is up.